Hi, my name is Nick Skok, and like what was just said, I'm a structural engineer at Degenkolb Engineers. And at my time at Degenkolb Engineers, I've had the opportunity to work on several analyses of pre-Northridge steel moment frame buildings. And today I was going to talk about how we've incorporated some recent research that's been funded by Peer into our evaluations of column splices in these buildings. So a little bit about the background of column splices and why we're interested in evaluating them. Prior to the 1994 Northridge earthquake, there were very few requirements in the building code that were stipulated for these connections. And as a result, engineers were providing the most cost-effective solution to create these joints, which resulted in partial joint penetration welds between the flanges and the webs. And since there were few requirements in the code before the 1994 Northridge earthquake, there's also a little guidance on the toughness requirements for the filler metal. So the combination of those two things lacked probably inadequate detailing of the actual splices. And then for earlier buildings, prior to having a large availability of commercial software packages for analyzing these building frames, approximate methods like the portal method were used to design these frames back in the 1970s and 1980s. And as a result, some assumptions behind that analysis led to the splices were located at inflection points to try and minimize the flexural demands across the actual splice, whereas, and only designed really for any sort of overturning axial force within the splice joint. And research has shown that, especially in larger, taller buildings, this sort of double curvature assumption in the frames may not be actually accurate. There could be cases where a column undergoes single curvature and the splice would have large moment demands at the joint. So the combination of the limited analysis capabilities that were done previously, along with the low weld toughness and limited connections that were provided at these joints results in brittle fractures at these connections when they undergo strong ground shaking, and that has been observed in earthquakes like Kobe in 1995. So this slide I'm trying to highlight, what do we see when we actually look at existing building drawings from before 1994? We see a lot of variability in the detailing of how these partial joint penetration welds were detailed, and that really is just attributed to what I was saying earlier about there not being a lot of specific guidelines behind these connections, so engineers could choose how they wanted to detail these to transfer the loads as they saw fit. At the bottom slide here, I tried to illustrate a rough timeline of when you start seeing different details become used for the partial joint penetration weld. At this timeline maybe makes it look like there's a somewhat clear break between different detailing uses, but really you can see there's also I would say that there's not a lot of consistency between decades of what type of detail was used. So how do we estimate the capacity of these connections? In recent studies in ATC 114 and now in the new AISC 342 code, there's this critical stress equation which helps you estimate the fracture strength of the PJP weld. And in that equation, considerations of the toughness of the weld filler metal and the fracture mechanics of having an internal flaw by the unfused flange are considered in determining that fracture-based capacity. And then the critical stress is then also capped by your more traditional weld type capacities that we do in design, where you're looking at base metal rupture and base metal yielding of the section. And then at the bottom here, this table is directly out of AISC 342, showing that there's a lot of variability in the toughness value that you use in this equation, depending on the actual Sharpie V-notch toughness value that you can find out in the building. So how does toughness affect the actual strength of these connections? So on these two plots, I've plotted the normalized critical stress with respect to the yield stress of the steel for varying flange thicknesses, and then the plot on the left is for a joint that's detailed with a square root of T over 6 plus an eighth PJP, and then on the right is for a detail that uses T over 2 plus an eighth inch weld. Now what you can see here is there's a lot of variability in the capacity that you see in the actual welds, depending on how tough the filler metal is. It could be a factor of 4 between the lowest values of toughness and the highest values of toughness. And then another way we could look at that is, how does the actual joint detailing affect the capacity of the connections? Does the detailing actually matter if we have a low toughness weld? On the left here, I'm showing different types of PJP joint details with their critical stress for a low toughness 5 foot-pound weld. And you can see that there's really not much difference between the actual capacity of those joints when you have a low toughness weld. However, when you start getting into welds with higher toughness, you can see in the graph on the right, you do get some improvement based on the detailing in your capacity. So how do we determine and analyze these connections in our modeling? When we're doing an existing building evaluation, we're typically using ASC 41 to do that evaluation. And in ASC 41, these connections are treated as a critical force controlled action. And then there's a couple, those are treated separately than deformation controlled actions in ASC 41. In a linear analysis, it's pretty straightforward to determine the critical stress. You take your gravity and seismic load combinations and just do a superposition of the demands at each column splice. However, if you start looking at these connections in a nonlinear response history analysis, the way you calculate the ASC 41 has you look at both the maximum demand in these connections from ground motions, and it also has you look at what's called the critical factored average, where you take the average response of the records and factor up that value, and you look at the worst case out of those two. So as you can imagine, in a nonlinear analysis, if you have a large building with dozens of column splices, and you're running 11 ground motions, you just start having to do a lot of data processing where you're looking at each splice throughout the ground motion record. And that can be pretty extensive outside of the model in terms of time spent, and it can use a lot of resources in terms of data hard drive space. So one way you can take advantage of reducing the amount of space and the amount of different time steps you have to check is you can create these orbit plots where this is like a section through like a 3D interaction surface of the demands that are seen by a column splice in the model. An alternative method that we employ besides checking the forces outside of the model in post-processing is we follow the ATC 114 recommendations for creating a fiber hinge that represents the actual column splice behavior at each location within the building. And to achieve this, we create a cross-section, we discretize it into overlapping fibers. And each fiber, we have a set of tension-only fibers that model the fracture mechanics of the steel material, of the weld. And then we have compression-only fibers to make sure we have adequate bearing and support after we see rupture in any of the tension fiber elements. The tension element, like I was saying, is capped at the critical stress determined from the equation shown previously. And when we're looking at acceptance criteria for ASC 41, we set the collapse prevention acceptance criteria at the point where the residual stress is hit, and then base all of our other limits thereafter before that point. And the advantage of doing a model like with fiber elements at these locations is it eliminates having to do this post-processing outside of the model that takes a lot of time and can use a lot of space on your computer. The one disadvantages of using this type of model in Perform 3D, you're only allowed to do 60 fiber elements, so you're limited in how fine you can discretize your cross-section, and you can't couple the behavior of the axial fiber with, say, the shear behavior of the column. So if you find in your analysis that you're expecting a column splice to fracture during a ground motion, you'll still be able to transfer shear through that column in the analytical model. But it can be useful to see how the drift performance of your building and what secondary mechanisms may form in your building after seeing how the column splices fracture during an analysis. And then this is just sort of an example of the types of studies we end up doing when we're looking at an existing building. We usually end up, like I've been discussing, since there's so much variability in the capacity of these connections based on the weld toughness, we end up trying to bound our analysis by looking at different toughness values to see how that would impact the recommended solutions that we're going to provide to our client. So you can see on the left here, if you have a Sharpie V-notch toughness of 10 foot-pounds, the bubbles here in purple represent the critical factored average DCR from an analysis. So all of those locations we would have to touch and strengthen, and that's approximately 2/3 of the entire splices in the building. But on the right, if we assume the weld toughness is greater and more on the order of 20 foot-pounds, that more or less eliminates the strengthening in the upper floors, and we now only have to strengthen half as many columns as we did in the 10 foot-pound analysis case. So it's really critical to try and nail down your assumptions on what toughness to use for that fracture material, and when determining the capacity or your fiber hinge model. And oftentimes when we go into a project, we try to assume towards the lower end, and then if design progresses, we try to get in there and do some material testing to understand what the actual strength of the welds are, and then we can refine our model and try to reduce the scope of our work. So with that, that's all I had. So thank you for this opportunity to present, and please let me know if you have any questions.